Good evening and welcome to the Linda Hall Library. I'm Lisa Brower, I'm president of the library, and on behalf of the entire staff, it's my pleasure to welcome you here tonight to this wonderful exhibition opening and our first lecture in a series that is devoted to the topic of atomic energy. I see a lot of new faces in the audience tonight. Louder? More volume? Is that what we're getting? How's that? Is that better? More? Okay, I guess I'm going to have to use my outdoor voice tonight. Anyway, we see a lot of new faces in the audience tonight, and I'd just like a show of hands. How many people have never been here before? In the library, yeah. Okay, well, anyway, if you are not familiar with the library and its programs, and you'd like to know more about it, there are several ways you can. You can fill out the sheet, the information sheet that was left on your chair, and drop it in the basket on your way home this evening. That will get you on our mailing list. You can also follow us on Facebook, occasionally on Twitter, at the iTunes store, and at our homepage, www.lindahall.org. So if you enjoy your experience here tonight and want to know more about the library and its programs, that's the best way to do it. So I would like to just give a few brief acknowledgments to all the people who made this evening possible. First and foremost, tonight's exhibition sponsors, Kansas City Power and Light, without whose financial assistance this would not have been possible. We extend a very big thank you to KCP&L this evening. Next to the co-curators of the exhibition, Nancy Green and Eric Ward, who put together a fabulous exhibition. I know they did a great deal of research, neither one being experts on atomic energy. I decided that they needed to brush up, and they did, and I think they came through beautifully. And they were also assisted by John Rollins and Sally Crossan and Eliseo Fernandez. And if I am forgetting anybody else, Donna Swisher also helped. But if I am forgetting anybody else, please know that you have my thanks as well. And on to this evening's lecture. I should say that this is the first in a series of 4 lectures, and the entire lecture series is also made possible by KCP&L, as well as the Victor E. Spies Foundation Bank of America trustee, Swiss Re, and the Linda Hall Library Annual Fund. And I think I have thanked everybody who needed to be thanked. In case I haven't, I thank you as well, if I have forgotten you. So let me not take up any more of your valuable time and introduce tonight's speaker, Dr. Jeff Wisoff, who serves as the Deputy Director of the National Ignition Facility and the Photon Science Directorate at Lawrence Livermore National Laboratory. Dr. Wisoff came to LLNL and NIF in 2001 as a Deputy Associate Project Manager for Systems Engineering. In 2003, he became the Associate Project Manager for Small Optical Systems on NIF, which included responsibility for the front end of the laser and laser diagnostics. From 2005 to 2009, he served as the Deputy Associate Director for Operations, managing the operations team that provides facility information technology, environment, safety and health, security, and administrative services to the Directorate. Dr. Wisoff received his bachelor's degree from the University of Virginia and his master's and PhD degrees from Stanford. And if that isn't enough, he also served as a veteran of 4 space shuttle flights, having been selected as an astronaut by NASA. Clearly a chronic overachiever. Dr. Wisoff has received a number of honors with NASA, including the NASA Distinguished Service Medal and 4 NASA Spaceflight Medals, and we are honored to have him join us here tonight. Please welcome him.
Thank you. Let me just get back to the title slide here if we could. So I'm going to talk tonight about if fusion energy is in our future, and I hope to take you somewhere tonight that's hopefully thoughtful but also fun. And I'd like to start by giving you kind of a perspective that I think astronauts get when they look back at the Earth, because what I'm really going to be talking about tonight is energy security and what should we be doing about it. I think, one of the first things that always comes to mind when I talk about what astronauts see in space and how that image of the Earth and what we're doing to the Earth reflects on perhaps what they might want to do with the rest of their career. People normally ask me, well, what qualifications does it take to be an astronaut? And that's this slide here, which you already saw. This is Ham the monkey. He took a trip into space, and you could see he was motivated by food. But what I want to talk about, this is a shot from my last flight in 2000 on the International Space Station, where we went outside and did some of the construction work in preparation for the arrival of the first solar arrays. But what you can see in this picture is the reflection of the Earth in my helmet, and you really do get that kind of full-faced view of the Earth and the big blue ball with the clouds. And one of the things that disappears when you're up there is country boundaries. What you see is really Mother Nature and the interaction between the forces that are going on the Earth with respect to Mother Nature. And the first thing you see when you look down is the great cities of the world, including this one, which was taken on my second flight in 1994. But you also see things that are a little bit more disturbing, such as the oil fires in Kuwait, which was taken by another shuttle crew during the Gulf War. And when you see things like this, you realize that there's a certain fragile nature to the Earth, and also a fragile nature to our energy infrastructure and the availability of energy. And it's fairly geopolitical in terms of how it's distributed, and such that there is conflict over energy. So what I want to talk about today is kind of the story of the National Ignition Facility and how that could impact our energy future, and in particular, your future as well. So let's give the abridged version of the history of the Earth to start with. And so if you think about, what's been happening on the Earth is, for many billions of years, life was forming, life was dying on the Earth, and eventually that turned into hydrocarbons and into our supply of oil and coal, et cetera. And then humans came along and started mining that and using it. And we've been using this system for about 10,000 years. And the question is, where are we going to go in the future? No matter what side of the argument you are on with regard to what carbon does to the atmosphere, eventually these hydrocarbons are going to run out. And at the same time, the evidence points to the fact that we shouldn't keep dumping carbon into the atmosphere. And so the question is, can we find another way of producing energy that can sustain us? And I'm not talking about energy that helps with, small blackouts. I'm talking about baseload energy, the energy that's there all the time, night and day, to power our cities, which is where our population centers are. So I'm talking about a big source of energy, something that has to be very robust, very abundant, and hopefully non-geopolitical. So let's look at kind of our, why I think that we're kind of facing a crossroads now and why we need to be thinking about this problem now. If you just look at the growth of population, that's certainly one trend which, underscores the need to find new energy. But there's other forces at work as well, and that is that the world population, as it grows, wants to have a standard of living similar to what we have in this country, and so the use of energy is growing rapidly as well as the population. Now, on this scale over here, this is world energy use in exajoules per year, and exajoules is 10 to the 18 joules. I tried to figure out how to put in context what 10 to the 18 joules is that people could associate with it, so I looked in Wikipedia. And I saw under Wikipedia, it says that 10 to the 18 joules is supposedly the energy output of the Starship Enterprise in the Star Trek series. So if you think about that and the way they can tug away from stars, I guess that's a lot of energy. But that's the only thing I can think of putting on that scale. The other thing to think about is the modalities of energy in the U.S. and kind of the time it takes to shift over. If you look here, what this scale is showing is that back in the 1850s, most of our energy, 90%, came from wood, with a small amount from coal. And as the years have progressed, we went through a period in the early 1900s where most of our energy came from coal, and then we've kind of flattened out where now we kind of have this triad of coal, oil, and gas with some nuclear and some hydro. But if you look at how we've progressed with regard to use of carbon, over the last 100 years, we went from 98% carbon, down to about 90% carbon. So we really haven't changed that much in our ability to move to carbon-free sources. And the question is, where are we going to go in the future? So for the first time, the energy fingerprint of humankind is really becoming evident in the way we're mining the earth, lighting up the earth, perhaps affecting the weather and the climate. And we're kind of at this tipping point where we have to think about where we're going to go next, because irrespective of where you are on the climate issue, we're burning about 10 million years of fossil fuel carbon every year, and it's just not going to last. We have to find another solution. And the reason I think that we have to start thinking about this now is that if you look at the retirement of electrical generation plants in the United States, from these sources, plants that were available in 2005, by the year 2060, much of the electrical generation capacity plants will have to have been retired and something else will have taken their place. So if from an economics point of view, if you want to switch over to some other form of power, we need to be thinking about how to build those plants now rather than later so that we don't end up building more coal plants and gas plants and putting carbon in the atmosphere. If we want to change that trend, we need to start thinking about it now. This shows the projection of, assuming that there's some move towards electrical vehicles, shows the trend in energy usage, whereas our ability to generate power will be going down over the next few decades. So we need a solution now. And the ideal solution would be one that's affordable, environmentally clean, non-geopolitical, inexhaustible fuel supply, non-proliferant, fit into the physical infrastructure that we have for delivering electricity now, compact and culturally acceptable, and deliverable and timely. And those are really tough requirements. And I think when you look at what's out there right now, there's really no absolute answer to this. There's not going to be one answer that's going to solve this problem. There's going to be a mix of solutions. But none of these solutions that are currently on the board can really get us to the replacement of baseload power and meet all of those requirements. The nuclear industry that's out there now, from the point of view of social acceptance because of the waste products, it's not clear we're going to be able to get there in terms of building those plants on the time scale that America is going to need them just because of the opposition to fission plants. And so I think we need to find another solution. And, we go back to Einstein. He had a lot of good ideas. And the question is there another idea? We think just as, fission plants depend on E equals mc squared. If you look, though, at a different way of using E equals mc squared, which is to take a hint from Mother Nature, when you look out at the stars, every star you see is being powered by fusion power. That is nature's way of powering the universe. And so this is what we are interested in talking about tonight, and this is what I think the National Ignition Facility can bring to us in terms of developing this power. So let me remind you about what fusion power is. Unlike fission power, where you take large uranium atoms and split them into smaller atoms, which end up eventually as nuclear waste, the idea here is to take very simple atoms, two isotopes of hydrogen, deuterium and tritium, which means they have a different number of protons, and combine them together. And this is what the reaction looks like. You have a deuterium nucleus that has one proton up at the top and a tritium nucleus down at the bottom, one neutron and two neutrons, and when they hit together, under high pressure and temperature, they fuse together and they form a helium nucleus and a neutron. So what you have left out of this reaction is a helium nucleus and a neutron. You don't have the long-lived byproducts of fission. And most of the energy is carried by that neutron. And so if you wanted to gather that energy up, what you would want to do is find a way of stopping those neutrons to heat a fluid and then use that heated fluid just like you do in a conventional power plant to drive a turbine. And that is what this talk is going to be about tonight and how NIF is going to lead the way to do that. So the question is, could we build a laser fusion power plant on Earth and have it provide significant carbon-free energy for all of humankind? And this really shows you the advantage. If you take 1 liter of heavy water, so that's deuterated water, it's water that contains deuterium, and you compare that to what you get out of gasoline, the energy content is equal between about a liter of this water and 2 million gallons of gasoline, and there's a lot of water. And that's where, this is where the geopolitical nature comes in. When you look at the world from space, you're no longer confined, to small regions of the Earth where resources are concentrated. You now have the resource of deuterium in the world's oceans, which are accessible by the world's population. So the question is, if this is such a great idea, why hasn't it been done before? Why are we waiting? Why does it take so long? Well, I don't know how many of you are cooks, but here's the recipe for fusion. You got to get the hydrogen from the water. That's not too hard. We could do that by filtering it out. But now you need an oven that's 100 million degrees. How many of you have a 100 million degree oven at home? You know, sometimes when you burn your cakes, you might think you have a 100 million degree oven, but that's not what you have. And so this is really the question, is how do you get to 100 million degrees and confine these atoms together in such a way that you can fuse them together and get the energy out? And you know, what you need to do is then bake them for a few billionths of a second. And that what will happen is that when those two atoms combine, the deuterium and tritium come together and combine, that helium nucleus that comes out and that neutron that come out have a different mass when you add them up than the original constituents. And that difference in mass has appeared as E equals mc squared. So that it comes out as energy. That mass multiplied by the speed of light squared, which is a very big number, gives you a lot of energy. And that's how you end up getting energy out that we can use. So the question is, how do we make, at the National Ignition Facility, a 100 million degree oven? So the idea here is, you know, the reason you have a stovetop and you have an oven in your house is that a stovetop kind of heats from one side, doesn't give you nice uniform heating. We want to use an oven where you can actually get uniform heating of a fuel capsule that we're going to then create fusion in. And so what we do is we use these little cylinders, we call them Holrooms. They're made of gold and depleted uranium. And what we do is we actually put a fuel capsule inside, and you'll see it as this movie runs here. The fuel capsule's about the size of a BB inside here. The capsule actually has a shell, and inside that is the solid deuterium and tritium. We cool this down to about 18 degrees above absolute zero, and it has DT gas in it. And we cool this thing down so that we have an ice layer. We bring the laser beams in. They heat the walls of the cylinder. The walls of the cylinder then become this X-ray oven. What happens is they start to emit X-rays that surround that capsule. And what happens is the shell blows off, and the opposite and equal reaction pushes the fuel in on itself and accelerates it to 1,000,000 miles per hour until you reach the conditions of 100 million degrees and 100 billion atmospheres of pressure where you actually fuse those nuclei together. The reason they don't want to go together is because those nuclei are both positively charged, and so they repel. And so you have to force them together with great velocity and pressure to make them get close enough that the nuclear forces take over and actually fuse the atoms together. So if you think about this, the way I like to think about it is you've all seen the shuttle go up, right? The exhaust comes out one end, it pushes the rocket up. It's that opposite and equal reaction of the exhaust. What you have here is a spherical rocket. You have X-rays coming in, bathing that capsule. The shell blows off. That's the exhaust coming off. The fuel inside is the body of the rocket. It's forced in on itself at such velocity that it overcomes that repulsion of the like charges in the nucleus and fuses together. And then you get the energy released. So how are we going to do that? So that's the idea. And now the question is, how do you actually do that? So what we've done out at the Lawrence Livermore Laboratory is we've built the National Ignition Facility, which is the world's largest laser. You can fit 3 football fields on top. Now, I figured that a winning team should have center place on top, so I put a winning team on there. You know, we got quite a licking out here a week or two ago. But that's how, you know, it's a big facility, about the size of a Walmart, you know, roughly speaking. And inside this building, we house the world's largest laser. This laser is made up of several components. These are the laser beam tubes here, and they're stacked in little 2x4 arrays, and there's actually 6 of those stacks going across here. So there's 48 beams here, 48 beams here, 48 there, and 48 there. We call this Laser Bay 1, Laser Bay 2. Then what happens is, in order to get those beams, you saw the movie where the beams kind of come in at cone angles into the cylinder. In order to do that, we have to break the planar geometry of these laser beams and reorient them so they can come into the target chamber from above and below. So the cylinder is oriented vertically in here, in the target chamber here. And so what we do is we bring the beams in, we steer them up with mirrors into the top, and we bring some of the beams in through the bottom, and the same thing over on this side until we have these nice cones converging in there. And what we deliver to this target chamber is 1.8 megajoules of ultraviolet light. It starts out in the infrared, and we convert it into the ultraviolet, and that interacts well with the target. And that's about, you know, roughly 50 times more energetic than any laser that exists today. And it's a power of about 500 terawatts, which is greater than the instantaneous power on the U.S. power grid, because what we're doing is it's actually about $5 of electricity to fire this laser. But what we're doing is taking all that energy and sticking it into a pulse that's only a few billionths of a second long, so it has a very high peak power, okay? So everything happens very fast, and that's because it's very hard to force these atoms together. And the reason lasers are such an ideal driver is that laser beams don't interact with one another. Photons don't interact with one another like charged particles do. So you can cram all the photons into a small volume. Laser beams can be very short in duration. You can actually get laser beams that are even much shorter than a billionth of a second. So you can get lasers to carry all that energy. You can get them to focus down into a very small volume, so you get a very hot oven that achieves these conditions that I said you needed in the recipe for fusion. Now, the National Ignition Facility was built by the National Nuclear Security Administration to do stockpiled stewardship. The idea here is that when we stop doing underground testing of our nuclear arsenal, in order to be able to know that the nuclear deterrent is viable going forward, because things change with nuclear weapons as they age, you need to be able to and somehow verify that changes going on haven't changed their properties as a deterrent. So rather than doing underground testing, what we do is the National Ignition Facility can do experiments that give you the conditions of nuclear weapons on a very small scale. We're talking about creating stars that are on the scale of a diameter of a human hair. We can measure parameters of that, out of that and put it into very sophisticated computer codes that predict the performance of weapons as they age. And this has allowed us to move from underground testing to a science-based stockpiled stewardship so that we can do responsible stewardship of our arsenal as we move forward. And so by investing in our nuclear security, we now have a tool on the behalf of the National Nuclear Security Administration that we can now use to explore how to solve our energy security. And so this is a very exciting tool. It's very unique in the world. There's no other facility like this, and gives the U.S. really a lead in the capability of producing this technology of fusion energy to bring to the world. And I think that the country that leads in the next carbon-free energy supply for the world will be the economic leader of the world. It's really important to be the leader here. So in terms of our mission space, we do global security missions. We do frontier science, because now we're creating the conditions that are in the interior of stars. So, if you want to study a supernova, you no longer have to wait for one to happen. You can say on Saturday night, I'm going to make one happen in the NIF target chamber by putting in an appropriate target that mimics the chemistry and the reactions that you would see in a supernova. And in fact, we have done our first science experiment in that area for a university researcher. And we have just finished concluding the review of about 40 proposals that were submitted for time on NIF to do groundbreaking experiments in many areas of science, including materials. How do the elements get produced in stars, the heavy elements get produced in stars as stars age, things of that sort. So there's a lot of very fundamental science that will be able to be done on NIF, that I think will be very exciting. And then, of course, there is the holy grail of fusion energy, clean energy, and the NIF can be used to do that as well. So, we believe that NIF will demonstrate the path to fusion energy. The way I like to think about the National Ignition Facility is kind of like the Wright brothers plane. The NIF is going to demonstrate the capability to do fusion in the laboratory. And then the question is this country going to invest in taking that discovery and using the NIF as a research front to go and develop that into something that can build practical fusion power plants? And we are very actively working with an internal team of about 30 people at the Lawrence Livermore Lab, funded on internal money, to lay out the baseline design of a fusion power plant based on what we're going to accomplish on NIF, so that when we get ignition, when we demonstrate fusion burn for the first time in the laboratory, it will be like our Apollo moment of landing on the moon, and we'll have a vision to put forward about how we can take that discovery forward and use it to benefit our country. So now is the time to put on your glasses. Now, the emblem of the Lawrence Livermore Lab should be on the outside when you put these on, so that you get the blue and red on the right side here. And if you put them on, I look like I'm in a 50s movie theater now. This is great. What I have is an animation of how the laser works, which will take you, we call it the ride, because what it's going to do is animate the laser beams going through the facility to the target chamber, and then it's going to spin around into one of the laser beams and take you with the laser beam towards the target chamber so that you can kind of see what's going on. So if we're all ready, I think we are. Let's see if we can get this guy going here. So what you're going to see first is the electrical energy. That's electrical energy going out to the flash lamps that energize the laser glass that amplifies our lasers. Then the lasers get injected. They go through those lit up amplifiers and go towards the target chamber where they hit the hull room and hopefully ignite the target. Now you're going to get kind of the 3D effect because we're going to move around and enter the beam tubes. We'll slow down the speed of light a bit here. And now you can feel kind of like a hamster running through a tunnel. But you can see the stack of 8 beams. They're in 2x4 arrays. It gives you a nice packing density for putting the lasers into the facility. Now you're traveling through the beam tubes. Inside these beam tubes, it's as clean as a semiconductor fab facility, class 100 or better, to keep dust off the optics. You notice the laser beams look like they're roughly 20 feet in length. That's because it's about a 20 nanosecond pulse, 20 billionths of a second, and that's a chunk of light that's about 20 feet long. And now we go to this area we call the switch yard. And in the switch yard, we split off the top 4 beams from that bundle of 8 beams and the bottom 4. And it looks like they're going to arrive at different times, but we've made the engineering of this facility so that all the beams travel over the same path length. So as they arrive at the target chamber, they're all going to time up exactly right and arrive together. Then we're going to convert the light into the ultraviolet, and then we're going to go into that target. And this is more or less a repeat of the earlier one where we now heat it up, the X-rays come in, we create the little spherical rocket, blows off, compresses the fuel, and boom, it goes. So the heating, so the pulse we send in there is on the order of 10 billionths to 20 billionths of a second. It heats over that time frame, and then when ignition occurs, it's all over in a few trillionths of a second. So everything happens very fast. You can take the glasses off. So I want to give you a little bit of a photographic a tour of NIF before I go on to kind of how we would then move on to a power plant. This is one of the laser bays of NIF. These are the beam tubes that you see here in the foreground, right along here. You'll notice that the beam tubes are high up off the ground. You got a person down here to give you a sense of scale. And the reason is the way our mission here is to get ignition, but transition NIF to a national user facility to be used for 30 years for research, whether it's energy research or nuclear security research or whatever. And in order to do that, you want to make sure the laser is easily maintainable, and you'd also want such a thing in a power plant. So this whole facility has been built on what we call the line replaceable unit concept. And what I mean by a line replaceable unit, if you all can remember before we had electronic cameras, the Kodak cartridges that you slapped in the back of your camera to be able to load it quickly, all of the optical components of this laser, of which there's over 6,000, have been prepackaged in cartridges so that a carrier can come underneath the laser, open a little trap door, pull out the old cartridge, shove in the new one, and lock it, and move on with life with operating the laser. And it's all done in a clean container so that it never gets exposed to the dirty air in the laser bay. So it's a pretty neat lock and load concept that really keeps this thing marching along. We started operating this laser. We had our dedication in May of 2009. And this is a brand new facility. We started doing experiments, target experiments, and hull room experiments that summer, and over the time frame up to last December, we had requested something on the order of 176 to 179 shots and got 173 of them, so I had about a 97% availability for a first-time commissioned facility of one of a kind of the sort, which is pretty amazing. So it's really been a very reliable workhorse. If you go to the target chamber, this is kind of what it looks like with the beams coming up and attaching to the target chamber. So each of these big metal tubes that you see coming up here contain 4 of our beams. And sometimes people don't even notice there's a person standing here. It's kind of like, where's Waldo? But each of these things comes in, it brings beams into the target chamber, brings them in those cones so that they can converge. And if you look inside the target chamber, this was early on when the target chamber was being built and the beams were being connected to it. You can see a person. This was actually, I think, on the cover of National Geographic or something. It looks like the human fly. And then in the operational mode, this is what it looks like inside. What you see here is that the aluminum walls, the target chamber is 10 meters across and is made of 4-inch aluminum. But we put on the wall what we call the first wall, which are these panels, which are louvered stainless steel panels, which catch any debris from the small target that's held inside, which is right here. And they also, because they're louvered, any light that's reflected tends to get diffuse and die away. You don't get any specular reflection down the beam tubes, which we wouldn't want. And what you see here are diagnostics. These are X-ray street cameras spatial cameras that you can see spatially what the X-rays look like coming out of this thing when you hit it with all these laser beams, and also take time history of it. And we also have a device here which looks back at our optics to make sure nothing's been damaged during the shot. So it's a kind of neat system, and it's all operational now. So, NIF is ready to do fusion experiments. This is a picture. We made the cover of American Physical Society. This is one of the implosions that we did at the end of last year. The idea here was that we are doing a very scientific-based approach to getting fusion. I think one of the misconceptions is that we know a priori how to make this work, so that all you do is build it, you stick everything together, fire, it should work. There's enough error in our understanding of the physical parameters and the codes that you have to bootstrap your way up. You need to measure things as you go along and modify the targets and the laser parameters to do what Mother Nature is telling you to do. And so we have a very systematic campaign that we're going through in order to achieve fusion, and this is kind of where we are in that campaign. The first is build the laser. I should say that there's 3 reasons put forward generally for saying that you can't get laser fusion to work. The first is you can't build the laser. Well, we've done that. The second is you'll never get enough X-rays in your oven that you create, because what happens is as these laser beams go into this can and heat it, it makes a plasma that tends to reflect laser light back out. And so the question is, can you engineer this in such a way that you can get a significant amount of the laser light to actually couple in and make X-rays? So that was the point of our first set of experiments we did last year, and we proved that we do reach the conditions that we need to get enough X-ray drive to drive this rocket, and that was completed last year. So then the next step is, okay, we've got an oven now that will give us the X-ray drive. Let's put capsules in it and make sure that we can drive these capsules spherically down, because this is the third reason why people say it won't work, and that is if you imagine squishing a water balloon in your hand, it tends to pop out between your fingers. Unless you get a very symmetric drive on this thing, it'll go unstable and squish out one side before you can compress it down to the conditions to get fusion. So what we did is, to start with, is we started with gas capsules, not capsules that have ice layers in them, which is what we actually need to do ignition. And we've proved that we had a lot of knobs to turn to get symmetry, and we were able to get symmetric implosions like the one that made the cover of the American Physical magazine there. What our next step is in the last few months, we have put in all the infrastructure into NIF to actually bring tritium targets in so that we can do deuterium and tritium targets. And there's actually a press release out today from NNSA that says, that talks about experiments we did last week where we took the first capsule that had tritium, hydrogen, and deuterium in it, created an ice layer that we need, such as like we need for ignition, inserted it in the into the target chamber and shot it with all 192 laser beams. Now that target was purposely dudded with hydrogen. It was not just tritium and deuterium, it was tritium, hydrogen, and deuterium. And the reason you do that is when you get ignition, you're going to have a lot of neutrons come out. That's how we're going to make energy with it. But those neutrons will hurt our diagnostics. And so what we do is we purposely dud the capsule so that we can keep our diagnostic suite in close to make sure that we're getting a nice symmetric implosion. Once we're convinced we have all the conditions we need for ignition, then we will pull much of our diagnostic suite out and rely on neutron diagnostics and shielded diagnostics in order to look at the actual ignition event. So that's where we're moving towards now. So the next thing that we need to do is start tuning this capsule up in such a way that the shocks that we create in it as it collapses down coalesce in the right way to achieve the conditions for ignition. And we will be doing measurements over the next few months to do that, with the anticipation of starting ignition experiments within the next year to 2 years. So that's where we are now, and we consider this experiment that we did this past week the beginning of the ignition experiment sequence. The actual DT burn experiments will happen when we know Mother Nature has told us enough to design an experiment to make it work, and that's a series of very deliberate experiments, and we believe we're getting very close. The way I liken the importance of last week's experiment is you've put the engine on the Wright brothers plane, and now it's time to tune it up so it can fly, and that's really where we are. It's a very exciting time. So let's talk about building a fusion power plant out of what NIF's going to demonstrate. So, this is just a graphic, kind of a schematic of what one could look like, where you have, essentially the same type of beams here coming into a target chamber. You have the balance of plant, your turbines, and you go out over the conventional transmission lines. Now, if you think about this more phenomenologically, about what this would look like, what you would need to do is you need to create power kind of like you do in a combustion engine. What you would do is you do shots at about 10 times per second. You'd create pops. You'd go pop, 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 and you'd be creating this semi-continuous stream of neutrons. Those neutrons would be absorbed in a thermal blanket here, and there's various salts that you can use to do that will stop the neutrons well. And it heats this up, and that fluid then runs off and runs a conventional balance of plant, whether it's a steam turbine or something more sophisticated. But this gives you a feeling of kind of what it would look like. This is showing it, I think I have an animation here in real time, so this is about 15 hertz, moving along. And so this is, quite a lot of horsepower. But, based on what we think you can do with these designs is you could, in a building about the size of NIF, build a gigawatt power plant, which would power a city like San Francisco in a building about the size of NIF. So, in a building about the size of a Walmart, you've got a gigawatt power plant. And, the other thing to think about is if you think about the alternatives, if we continue to burn carbon-based power sources, you're talking about 7 million tons of CO2 per year for every gigawatt power plant. And as I told you, we're going to be retiring many power plants in the United States over the next few decades. We've got to figure out what we're going to replace them with. So from a policy point of view, where we are on this, the Energy Secretary, Stephen Chu, has announced a National Academy of Science, National Academy of Engineering review of what the go-forward laser fusion program, inertial confinement fusion program should be in the United States. Right now what we have is the NIF. We have this incredible gem of an asset to go do this, but we actually don't have a national program to go and develop fusion energy. And so that conversation will probably start in the November timeframe, and the National Academies will make a recommendation. And as I said, we have a team preparing for that in order to present a viewpoint about how quickly we could go. And our vision of this is, we get ignition on NIF somewhere in the 2010 to 2012 timeframe. You could build the first power plant. We call it a laser inertial fusion energy, or LIFE.1. Would be built in the early 2020s. What you'd do is there's a few technologies you would need to work on before you built that plant, and then you'd bring them together and integrate it in the first prototype plant. And then you would have the first commercial plant in 2030 with hopefully a significant fleet incorporated by 2050, around this time where all these other plants are going offline. We have started talking very vigorously to the power companies. We have regular meetings with CEOs from the power companies. They are very interested in a game-changing technology, because replacing the baseload electricity that powers our city is something that's a very hard thing to do. And there will probably not be one solution, but we think fusion energy could provide one of the best solutions. And so, from our point of view, we're sitting at kind of this crossroad where we can, as a nation, commit to going down and developing some new technologies and trying to show that these are practical technologies that can be developed and deployed, or we can continue down the path of waiting, in which case we think the clock will run out based on all of the trends that I've talked to you earlier. And, I think, again, getting back to the perspective of kind of an astronaut, if you could imagine yourself standing in the moment of time of the Wright brothers plane, it's hard to imagine that in 30 years you could have seen how the world was going to change. This is the DC-3, which is generally credited as being the first practical airliner that really brought the airliner industry into existence. And it happened in 30 years because the country made investments in aircraft technology, largely for defense reasons. But that investment paid off in terms of creating the civilian air transport. And it's hard to believe that, I don't think standing in that moment you could have possibly imagined that before the end of the century, this was from my flight, I'd be able to look back and see Kitty Hawk from that viewpoint. Norfolk, Virginia is my hometown, so I'm assuming I took this picture, but I don't know for sure. But you can see Kitty Hawk here from space, and it's, I think we limit ourselves when we say it's not doable because it's hard. People have been working on fusion energy since the invention of the laser. 2010 is the 50th anniversary of the invention of the laser. In fact, you have it in your history out there in the displays. And shortly after it was invented, people realized that this could be a driver for fusion energy. So the search for fusion energy has been going on for those 50 years, and it's always seemed like it was over the horizon. Now we believe we're on the verge. I think we're living in that moment of the Wright brothers plane, and I think America needs to lead in this, and I hope we will have the wherewithal and the vision to do so. So I'd like to end with, let's invent the future together, and I want to thank you for your time. I also have two copies of a book that was put out at our dedication called The National Ignition Facility, Bringing Star Power to Earth, that I'd like to give to the library so that people want to see pictures about the history of how we got to NIF, because it's actually the culmination of a large number of laser systems that were built at the Lawrence Livermore Laboratory, and hopefully you'll enjoy these.
And thank you for the books, and they will be available for circulation soon. Any questions?
When you say NIF ignition, is that first fusion?
Yes. So I probably should have been more explicit in that. When we talk about fusion ignition, what we're talking about is when you create the conditions. People have taken lasers before, including at NIF, and produced neutrons from fusion events. What happens is you collapse these capsules, you'll get a few fusion events that occur, and the neutrons will come out and you can detect it. But to get a self-sustained burn where basically it is burning because of, when you create those helium nuclei, which are also called alpha particles, those alpha particles, if you get a dense enough plasma, those alpha particles will contribute to the heating, and as you create fusion events, those alpha particles will further heat the plasma and create more fusion events, and you get a self-sustained burn, in which case you go from, you will generate a lot of neutrons. In the press release that was just coming out of NSA today, we generated on the order of about 10 to the 13 neutrons, which is 1,000 more than we had generated before in the facility. But we will go, when we actually get ignition, we'll go many orders of magnitude above that as well. So, we do create fusion events, but it's a question of a self-sustained fusion event, which is what ignition is.
When do you think that will happen?
I think that'll happen in probably the next year to 18 months.
Thank you, thank you. You've honored us with your presence. I'm really curious how we can help you get this story to Washington, because you've got to have big funding and it can't be tentative. How can we help you do that, and can we get you on the road every day?
I think, well, believe me, my director, Ed Moses, is working hard at this, but we're at an interesting time because, we're in a time where we're budget challenged, and so I think there are many believers out there in fusion energy, but in the government, what they want to do is they want to see us get ignition first, before we go and do it. And so, I thought it was, very visionary of the secretary to put forth, let's get the National Academy study going, assuming we're going to be success, so that we can start this conversation now, so that when we get ignition, perhaps we will have a determination of where we should go. I do think that it behooves us, with the effort that we're doing, to continue to work very hard on putting forward a vision that's credible, that answers all the questions, so that the National Academy will have a complete story. And that's what we're working on, because we want to work on presenting the best case we can, that this is not something that we should put off and continue to work at a low level for decades. This is something that we should do in a more daring way and invest resources to go off and do, because we're facing such pressing energy security needs. And I think this is a great story. The nation has invested in its national nuclear security through NNSA in this great facility, and this is a chance to leverage that facility to attack yet another big security problem, which is energy security. And that's a great story.
Yes. Well, let me say I'm amazed and impressed, and I think most people here can see that this is a remarkable achievement, and you're going great guns. The question I have is, as you know, there's been a large number of naysayers about nuclear energy from the concern about radioactive waste and things of this nature. Can you say a few words about how this process, and I'm not concerned about it, I think I understand, but how do you address the concerns about not having radioactive waste that has to be disposed from this like a normal fission plant? Because if you can persuade people that this does not produce such waste, I think you're 90% there.
Right.
Thank you.
So I got a couple answers to that. I think, I think it's very hard in this environment for Lawrence Livermore Laboratory to come forward to the government and say, you should build this because we say it's great. What we need is pull from constituencies that see the benefit of this, the power companies, the people who are concerned about the environment. So we are speaking to all those folks and showing them and letting them make their own determination about the viability of where we are and the readiness to go forward. And that conversation continues today. There is a part of the story I didn't talk about, which I think is also interesting, and that is, I talked about a pure fusion plant, about how to take this technology and generate neutrons, which we then stop in a fluid, which gets hot, and then you drive a steam turbine or something of that sort. There is another version of this that we've talked about and we continue to work on, which is a hybrid. If you think about a conventional fission plant, what happens is you bring together nuclear material, uranium together, it creates its own neutrons and it drives itself, and so that's why you have to have control rods and things of that sort to make sure you don't get a runaway effect. It's not passively safe, you have to actively control it. And what happens after a period of time is as it breaks down into its constituent atoms, you get less neutrons produced, and so it self-poisons, and you have to take it away and reprocess it and bring it back in order to use it again. And during that time it's out being reprocessed is where the proliferation concerns are, that people will remove weapons-grade material that's been generated in those rods, okay? If you had a separate source of neutrons to drive those fission reactions, you'd never have to take the material out, and it would never self-poison, so you could burn up all of that fissile material. So if you could imagine taking a fusion engine, which is generating all these neutrons, and putting a fission blanket around it, it never has to be a fission blanket that's a critical mass of material, so it's still passively safe. Those neutrons will break down that fissile material and add gain to the overall system. You'll get more energy out. So it takes away some of the requirements for the fusion engine, adds gain, and it burns up any kind of fissile material. You could put the world's nuclear waste into this thing and burn it up and get energy out of it. So there's a lot of ways you could play this technology that are interesting, and I think this is one of the discussions that has to go forward in the appropriate forums to decide, what do we want to invest in?
I imagine the Pentagon is very interested in your roaring great lasers. Is weaponizing them part of your mission as well?
No, it's not. The NIF lasers, first of all, given the size of them, I'm not sure they would make a very good weapon. But it'd be kind of hard to move around. But I think the concern is a valid one, because it is true that when you, as laser fusion power plants develop and you have big lasers like this, laser technology is going to spread around the world. But I think that's going to happen irrespective of whether that happens through these fusion plants or through other. Lasers are becoming common everywhere. There's more concern about weaponizing stuff you find in welding plants, because that technology is available to everybody. And as those lasers become more and more powerful, they can be fooled with to be used for other purposes as well. And so I think that, although I think it's a valid concern about where these lasers would end up if you built power plants out of them, I think the technology, by the time we get there, that technology will be fairly all around the world already.
Yes, sir. You described the fuel capsules as depleted uranium, and then with a drop of the good stuff inside them, and a stream of them running through this reactor. Could you comment, does depleted uranium bombarded with neutrons create a waste stream?
So the idea, but let's make sure we are on the same page. So first of all, the depleted uranium is in the cylinders, okay? And then the capsule is inside of that. The reason we use depleted uranium now is because we're an experimental research, and we want to pull out every stop to give ourselves every advantage of getting to fusion. So this gives you the best conversion of the laser into X-rays to drive that oven. We assume that when we get this working, that we are not going to be fortunate enough to come up at the optimal design the first time around, and so that we will be developing more efficient targets over time as we understand the fusion process better, and that we would not use uranium hull rooms in the final in the fusion power plants. What you would want to use is a very cheap material. You'd want to get the price of targets down to something on the order of a quarter in order to make fusion power competitive with power industry, because you're shooting these things 15 times a second. You go through millions and millions of these targets. And if you look at the cost of the materials in targets that we make today, you can hit that price point if you can remove all the touch labor, because the cost of the materials that are in the targets is just pennies. And the question is, right now they're research targets. So these targets that we make are very sophisticated because we make them in such a way that we can change the properties of the targets. As I mentioned to you, we have to engineer our way to fusion. So when we do measurements, we may want to change the size of the hull room, make it longer, make it narrower, make it out of a slightly different material, put a different coating on it. And so we make our targets in a modular way that allows us to do that. By the time you move to a practical fusion power plant, you will have locked all that down. You'll say, this is the target I want to use. I know how efficient it is. I'm going to take out all those degrees of freedom, and I'm going to make a really dumb, simple target that I can stamp out of, something equivalent to stamping out Legos, hopefully. And so from a price point of view, you would not, from a practicality point of view, you wouldn't be going there long term.
Just a brief clarification of an acronym. LIFE, laser, eye, fusion energy, what is the I standing for?
Laser inertial fusion energy. And inertial is because everything happens so fast that it stays in one place and doesn't come apart. Right.
At this stage, at the experimental stage, you're really working on a batch process, one at a time. As you move to a continuous process, is the concept that the capsules go into the chamber, but are the lasers then burst lasers, or is it continuous laser? And if it's continuous, what's that do to your energy input?
Right. So it would be a burst laser. The idea is this would be more like an internal combustion machine where you're running off a series of small explosions. So what you'd be doing is firing the laser at about 10 to 15 hertz, so 10 to 15 times per second. And what you would do, the way the targets would go in is they'd be shot in like skeet targets. The laser beams are traveling at the speed of light. What you would need to do is track the targets, shoot them when they get to the center of the chamber with the lasers, and so you're running like this. You're going pop, 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 15 times a second. And so the targets themselves would be essentially in a target injector with a factory there that's creating the targets and putting them out in a continuous stream, as you go through. So the energy for the lasers would still be very similar to what we're running now. It would be somewhere on the order of 2 megajoules of ultraviolet energy.
What was the budget for this?
So the National Ignition Facility cost $3.5 billion, and then the National Ignition Campaign, which is a multi-institutional program, which is, the National Ignition Facility built the laser and the target chamber and a few of the diagnostics, but then everything else you need to actually get ignition, like the targets, the personnel protection systems that went into the building to surround the target chamber for the neutrons, the target development in physics, the diagnostic suite to do ignition. That's a multi-institutional campaign that's roughly $1.5 to $2 billion, and it involves Los Alamos and General Atomics and the University of Rochester Laser Energetics Laboratory and Sandia National Laboratory. And we have important strategic relationships also with universities around the country, such as MIT and international agencies like the CEA in France and AWE in Great Britain. So there's a lot of partnerships around the world that have helped make NIF what it is today.
Yes.
I'm sorry.
I'm sorry.
Go ahead back there. I'll come back to you.
I can't help but think that inside this reactor is going to be a huge X-ray and neutron flux. Isn't that going to induce some radiation in the materials around and of the reactor?
So there's two issues you have to deal with. One is the lifetime of the target chamber wall, which is one of the things that we're working on the design, and the other is secondary activation, which is what you talk about, which means that you need to design an area, much like other nuclear reactors, where people can't go for the time it's operating. So yes, that's true. There's an areas you can't go. And in fact, in the NIF, when we get ignition, it'll take about 5 days before you can go back into the target chamber area to do anything in there while the secondary activation comes down. So you have to design your power plant, just like a nuclear power plant, to be able to sustain those kinds of fluxes, or design them in such a way that the components can be changed out once they wear out.
We're all aware of the colossal failure of the political system in the Super Collider project, and now it's turned into an amusement park or whatever it is right now. Given that the NIF has the potential for doing scientific experiments, what do you think that we might gain from that, and what do you think we're going to lose because the inability to have that neutron facility that we would have had in the Super Collider versus CERN, I would say?
Let's see. I'm not sure I'm interpreting your question. I think your question is if we do science on NIF, how much that will detract from doing other types of...
No, not
okay,
detract,
okay.
but what are we capable of doing with NIF that we would have been able to do with the Super Collider, and what are we missing that we would have not been able, we can't do now because we don't?
Well, the Super Collider was really more designed to look at fundamental particle physics and the fundamental constituents of atoms and finding new particles. NIF is really geared towards creating the conditions of fusion burn so that we can do our stockpiled stewardship mission, do our basic science mission, and do our energy mission. And the plan for the user facility is that there'll be we're actually in the process now of getting the governance plan through all the approvals, but the idea here is that it would be a peer-reviewed process. People would have experiments they would have put on NIF, universities, other types of agencies. They would go through a peer review process. The best proposals would be picked, and then the time would be worked out to get their time on the facility, and the percentages will be probably something like 85, since the facility is an NSA facility, about 85% of the work would be for NSA, and then the other 15% would be available for these other purposes and missions.
Hi, I'm not exactly a naysayer. I think you've created a marvelous thing, and it's wonderful for basic research and everything. But I'm a power engineer. I built 27 nuclear power plants. I even built a fusion plant at Princeton, TFDR. I know what it takes to go from technology to commercialization. My comment is, like I said, it's a wonderful scientific piece of equipment here, and it certainly should go ahead with the scientific research. But it's so big, so complex, and so expensive, and you're so far from commercial operations that to throw it out as kind of a bone for us, I would predict with some confidence that no one in this room will live to see this commercial plant. And part of it is you can't see how to get where you are to the commercial plant. Nuclear power was easy. I mean, within a few years, you could see...
Well, I disagree with the last statement. I mean, that's the point of this team of 30 people we have, is that we actually have designs that we're working on for how to get there from here, including we have the design for the laser that we think will work, that will run at 10 hertz at these power levels. We have demonstrated already at General Atomics inserting targets in a target shooter at about 6 hertz with the targeting requirement, with the accuracy needed to do what we need to do. So in fact, I think there's a more clear vision how to get there from here than there was when the Wright brothers plane flew to get to the DC-3, because I don't think you could have imagined a DC-3 the day the Wright brothers plane. We can imagine how to get to a fusion power plant, and we know which technology problems we have to work on, and the approach we're taking is not to assume a miracle out of NIF to get some gain that we aren't en route to get. We're basing our plans on getting gains that we think we can demonstrate on NIF so that they can be directly applicable and taken over to the next phase. But you're not going to go directly from ignition, in the next 2 years to building a power plant. What you need is a concentrated technology development plan of about 3 to 5 years on a certain set of questions, which we are going to be taking forward to the National Academy of Sciences to show them what they are, and a roadmap of how to get there. So, and also I think it comes down to commitment. At some point, energy security is going to become such a big security problem for this nation that we're going to have to decide, is it worth something on the order of a Manhattan Project? Now, I'm not saying that that's where we are now, but I'm saying at some point we have to decide what sort of resources we want to put on solving this, and is this the right play to do? And that's what I think the National Academy of Sciences have to weigh in. That's what our peer review has to weigh in as we talk about this in scientific forums and present the plans that we have. I don't expect anybody to take our word for it. This has to go through peer review. It has to have the skepticism of the scientific community. We want that, and we welcome it, because that will only make us be able to go faster, because we'll identify the issues faster, and we'll be able to move that much faster on solving them.
I know there are several more questions, but this will have to be the last one, and I'm sure Dr. Weisoff will hang around for a couple of minutes to chat with people.
I'm curious about the BB-sized container that holds the deuterium tritium. I was wondering under what gas pressure it's at, and what percentage of that gets
So it has
fusion.
So it has what it is it has a we take the capsule and we put in about 150 micrograms of deuterium and tritium, and we cool it down to 1.5 degrees below the triple point. So you actually have solid deuterium and DT and gas phase in equilibrium with one another, okay? And what actually happens in these capsules, which is kind of interesting, is the way you get a nice, perfectly spherical layer inside is that as the tritium undergoes beta decay, it locally heats an area, which will then evaporate that, make it move to another part of the capsule, and so it naturally distributes itself along the isotherms so that you get a nice distributed capsule there. So the amount of deuterium and tritium in there is very, very small. And the capsule is about 200 micron wall, and it's about 2 millimeters in diameter. And the capsules we're working with right now are made of plastic. We also have designs that could use beryllium. And so we have a couple options. Right now, the plastic capsules are working real well, so we're working in those. And if we have any issues with those, we have another design that we can go to. So roughly, I don't remember the numbers, but I think it's on the order of, you'll burn something on the order of 30% or something of that sort when you do it, because at some point the capsule comes apart, as you burn. But I don't know the exact number. I'd have to go back and check.
Thank you, Dr. Weisoff.
Thank you.
And thank you for attending tonight's lecture. Please pick up a white postcard with information about the next 3 lectures. Next week, same time, October 13th, 7 p.m., Richard Rhodes. Thank you and good night.